welcome to Learners Hub. This is Alvin for you. So in this tutorial you are going to learn the topic related to fins or extended surfaces, which comes in the subject of heat transfer, and it is more important that we understand the basic concepts of fins before we get into the analysis of fins. So let us not waste much time, let's get into the topic.
So in this tutorial video you are going to learn something about fins, which is also called as extended surfaces. So let us consider a simple example of a hot body. Say its temperature is at Tb, which we can take it as base temperature. So if you keep it in air, the heat will be transferred from this hot body to the air by convection process, which involves H and T infinite, which is surrounding temperature. Now suppose if you want the Q to be increased to a great extent, say if you want to cool down the hot body, then the only way is to increase the value of Q. If it has to be increased, then we can refer the formula what we have, or the relation Q is equal to HA delta T. This is nothing but something which you have obtained from Newton's law, which governs the convection process. Here we have three terms, H delta T and A. So the thing that we are going to do here is to choose the term A and increase it so that the value of Q also increases proportionally, because here we already have a surface area called A. For example, if I mark it like this, convection happens from the surface that is exposed to air. Here we will consider it as A. If we can increase this value of A, the value of Q can be proportionately increased. According to Newton's law, as you saw, that area is present in the numerator on the right hand side. So how do we do that, or how do we increase the area? Say if this is the hot body that is considered, the already existing area is A, as I already shown in the previous diagram. In this diagram there is a small protrusion which comes out from the surface. This protrusion, what is coming out, is what is called as the extended surface. This protrusion will cause the area to be increased in its value. The red one and the black one added together, the shaded ones, will give us an increased area, due to which the convection can happen from throughout the extended surface as well as the already existing base area. Hence the value of Q will be increased rapidly. This extended surface is the one that causing the Q value to be increased, which is called as fins. Some of the examples what we can see of fins are like IC engines, condensers, radiators, and also in heat exchangers. These are the some components what we find where the heat has to be exchanged at a rapid rate, or the cooling has to happen at a rapid rate. Here you see IC engine of our two-wheeler, and then if you have a look at here we have the condenser model. You might have seen this in the old refrigerators, where behind the refrigerator you would find the condenser tubes, along which the tubes will be attached with number of small rods. These rods are nothing but these are attached to these condenser pipes to increase the area so that the heat is transferred from the condenser to the atmosphere at a rapid rate. So increasing the surface area will always lead to increase in the value of heat transfer. Having so many applications, it becomes so very important to have the analysis of all these fins before it is designed for the purpose. So the analysis of fins, what we see here, can be splitted up into three different cases or assumptions. So what are these assumptions? We'll have a look at it one by one. The first thing is that we are going to assume the fin to be infinitely long. And the second case, we assume the fin to be short fin, which means the length is known but the end is insulated. And the third case, we consider the fin to be short fin again, but the end is not insulated. These three cases can be represented by the drawings what you see here, that an infinitely long fin is simply that we assume the length of the fin is increasing till infinite, which is practically not possible. It just means that the length of fin is more. Next is the short fin. You have the end insulated, which means the tip of the fin will be insulated by an insulating material, which means the heat loss at the tip will become zero. And next we have a short fin with the end not insulated. The meaning of short fin itself is that the length of that fin is known and it is of a smaller number compared to the base body. You will find all these formulas for 3 different cases in the data handbook of CP Kothand Raman. I am using 8th edition, and you will find these formulas for extended surfaces in page number 50. The formulas for temperature distribution, heat transfer rate, and efficiency effectiveness will be obtained here. Here you see the formula for temperature distribution in the second column. The first column says what type of fin it is. It is a long fin in this case. Second column gives temperature distribution, and the third column gives the value of Q. It repeats for short fin, end insulated, and also for short fin, end not insulated. Now let us look into a problem to understand this concept in a much better way. So we have a steel rod of 12 by 12 mm, length 159, protrudes into air at 35 degrees Celsius. The furnace wall temperature is given, the thermal conductivity is given, and convective heat transfer coefficient is given. So we have 3 sub questions. We'll look into it one by one. So first thing we do here is that note down the given data one by one, and then we proceed to understand the question what we are supposed to find it out. So base temperature is given as 200 degrees, surrounding is 35 degrees, that is T infinite. Thermal conductivity is represented by K. Heat transfer coefficient is given as 22 watt per meter square Kelvin. And then we have the length of fin given, which is 159 mm, and the cross section of the fin is given as 12 mm by 12 mm, which is a square cross section. Now what are we supposed to find? The first sub question says you are supposed to find the temperature at the end of the fin. So that is called end temperature, which we'll take it as T at x equal to L. Next sub question says you need to find out the temperature distance of 80 mm from the base. That is T at x equal to 80 mm, and the last one is T at, if you assume the length of fin as 80 meters, then what is the temperature over there? We'll represent the whole thing in the form of a sketch. So we have the base of the furnace wall at 200 degrees Celsius. We have the fin, and the cross section of fin is known as 12 mm by 12 mm. And then the data that are given are with respect to convection. The value of H is given, and the value of T infinite is given, which is surrounding temperature 35 degrees Celsius. The length of fin is also given here as 159 mm, which means that the fin can be considered as a short fin because the length is mentioned. So we have the boundary of the fin from x equal to 0 to x equal to L, and the length varies from 0 to 159 mm. We know the value of m, that is given by HPKA power 0.5, which you will find it in the data handbook, page number 50. First we will find out the perimeter. The value of P is called perimeter. Here it's a square cross section, so perimeter is given by 2 into A plus A, which you can find it out in this manner. Next we will find out the cross sectional area. Since it is a square cross section, the area will be given as A square. You can substitute and get the number. K is directly given, H is also directly given. So now we'll directly find out the value of M, which is given by that is P value, and then H value. You can write the K value and then the area value. Multiply them so that you get the value of M as 11.82 per meter. The unit of M is per meter. Now going on to the first sub question, we need to find out the temperature at x equal to L, that is the end temperature. We know the temperature distribution formula, which is given here, which I'll show it in the data handbook in the later stage in this video. You'll get the temperature distribution formula like this. Remember, it is cos hyperbolic. So that is a Tx, that is temperature at any distance x. Here we are taking the value of x as L because we need the end temperature. T infinite is known, Tb is known. You can go on substituting it. Remember, it is cos hyperbolic. I repeat it again. While using calculator, make sure to select cos hyperbolic. So calculate this. The only unknown here, T at x equal to L, will be obtained as 107.38 degrees Celsius. Going on to the second sub question, here it is, they've asked you to find out the temperature at a distance of 80 millimeters from the base. So we have the length of fin, the total length of fin is 159 mm. What is asked in the second sub question is you need to find out the temperature at a distance of 80 mm from the base, that is at x equal to 80 mm. We know the temperature distribution formula once again. There is a short fin as I already mentioned. So we take the formula, assume it to be short fin end insulated, and then we have the same formula like previous one, but here the value of x will be 80 millimeters. Substitute the value. Sorry, the upper part is slightly cut. Substitute the values, use your calculator, you get the value of x at 80 millimeters as 107 degrees Celsius. This you will find it in the data handbook on the same page number 50 as you see in the picture now. We take short fin end insulated, which is a general assumption which we take until and unless the condition or the case is mentioned in the question. So the third sub question says the length of the fin is 80 meter, which is quite long when compared to the wall and the already length of the fin that is mentioned. So we assume the fin to be infinitely long, which is case number 1. As I already said, 80 meter is quite long when compared to already existing length of the fin, that is 159 mm. So we consider this one to be infinitely long fin, for which we have the temperature distribution for infinitely long fin like this. Which you will find it in the data handbook once again in the same page number 50 for infinitely long fin. You can go on substituting the values. And finally, you will get the unknown parameter. Temperature at a distance of 80 meter will be equal to 35 degrees Celsius. Now all of you can have a look here that the temperature at the infinitely long distance is same as the surrounding temperature. As the length of the fin increases, the tip will never get heated because the length is quite long. Once again, as I mentioned, the formula is obtained in page number 50 in your data handbook. The page number will vary depending on the edition. You can cross check it by turning the pages. So this is the 8th edition. You'll get it in page number 50 for long fin. The second column gives you the temperature distribution. Now let us discuss one of the important parameter of fin, which is called fin efficiency, represented by eta. Let us assume a base which has a fin. We'll take the length of the fin as L, base temperature as Tb. This fin is exposed to surrounding, which is at T infinity, and a heat transfer coefficient of H. Now, since it is a solid material, as heat is transferred through this solid material, you would see that this solid material will offer a resistance. This resistance is called as the thermal resistance. Because of this thermal resistance offered by the solid material, the temperature will not be same at the surface. This base temperature will be higher. By the time it reaches the surface, it will be Ts. Note that the Ts temperature will be less than the base temperature. This is due to the presence of thermal resistance. This is a practical scenario what happens. Using this, how do we write the efficiency? The efficiency can be simply written as the ratio of two terms. The amount of heat transferred by the fin, actual transferred by the fin, over the amount of heat maximum transferable by the fin. So basically there will be maximum heat transferable by the fin and actual amount what is being transferred by the fin. So when do we have the maximum heat transfer in a fin? It happens only when the fin is having the base temperature throughout its surface. which practically doesn't happen. This happens only when the resistance is 0. Now for having an expression for this value of fin efficiency, we are going to consider the same 3 cases what we dealt in understanding the fin. The first assumption would be infinitely long fin. Second assumption would be short fin, but end will be insulated. And the third case will be short fin with end not insulated, end or tip. So as I told, the second case will be end not insulated. So let us just take the first case and see how we'll get the expression for the efficiency. The heat transferred by fin divided by maximum heat transferable by the fin. So heat transferred by the fin, you will get this formula. Since we have it's derived already, you will get it from the data handbook in page number 50, divided by the maximum transferable heat. I've already told you how you are going to get maximum heat. It happens only when the complete fin is at the base temperature. So this fin will transfer the heat to the atmosphere through the mode of convection. So therefore, from Newton's law, we have the formula for heat transferred by convection as HA delta T. We can rewrite it as H into PL delta T, where P is called as the perimeter. So perimeter into length will give you the surface area. So we are writing HA delta T in the form of HPL delta T. So the terms that cancelled are temperature difference, and HP by HP is there, but in the numerator I have HP per 0.5. So finally you will get the expression as Ka by HP power 0.5 into 1 by L. So we all know Ka by HP is nothing but 1 by M, because M is given by HP by Ka. So we can rewrite this as eta equal to 1 divided by M into L. That will give you the efficiency if you are considering the fin as a infinitely long fin for case 1. Now similarly, when we write it for the remaining 2 cases, if I write for case 2, that is for short fin and insulated, we'll get the value of eta like this. And when we write it for case 3, you can write the expression, divide and cancel the terms and rearrange the terms. You will get the expression for efficiency in this manner. While the denominator remains same in all 3 cases, that is a maximum heat transferable. So in all 3 cases, the one that changes will be the numerator, which will get it from the data handbook. So this is the formula, I will get it for case 3. So as I told you, to get these formulas, you can refer the data handbook by C.P. Kodandraman, 8th edition. You will get it in page number 50. If you look for other editions, you are going to get the same formula but different page numbers. So one more parameter which is very important while analyzing the fin is called as fin effectiveness. This is a parameter represented by the symbol eta. So this fin effectiveness is simply means that the effect of fin. What is the effect of having a fin on a surface which is at higher temperature? So we'll be able to calculate this effectiveness of fin with this expression given by eta equal to the heat transferred with fin over the heat transferred without fin. So this would give us the effect of the presence of a fin. So we'll just understand it in a much better way with this example. We'll consider a fin which is attached to a base. Let us assume the base temperature to be Tb, this fin to be exposed to surrounding at T infinity and H. So here we have the fin. Let us consider another example where the same base with the same temperature of base temperature of Tb is exposed to surrounding at T infinity and H. Now this does not have a fin. This is the example of heat transferred without a fin, and the first one is for heat transferred with the presence of fin. So this will give us the heat transferred with fin, and this will give us the heat transferred without fin. By taking the ratio of that, we'll get the value of effectiveness of the presence of a fin. Now remember that if at all the fin is effective, like what is the purpose of fin is to increase the rate of heat transfer. If at all the heat transfer is increased due to the presence of fin, the effectiveness will be always greater than 1. In case you get less than 1, it means that the fin is actually reducing the heat transfer, which is not desirable. We attach the fin to a hot body in order to increase the rate of heat transfer. So the effectiveness should be greater than 1. Same like how we considered efficiency in 3 different cases, we can consider the effectiveness also in 3 different cases. So if you consider case 1, infinitely long fin, the heat transferred with fin will be numerator and heat transfer without fin will be denominator. Heat transferred with fin will be given by, for a long fin it will be given by HPKA power 0.5 into the temperature difference, which you have derived it assuming the fin to be long fin, divided by, if there is no fin present, it will be directly due to Newton's law, that is HA delta T. In the same way, we can also write down the expression for effectiveness and calculate it for short fin end insulated and short fin end not insulated. For any doubts or clarifications, you can drop a comment or contact me through my mail ID.